So the second speaker for this morning is Giblin Sensei. Peter was my PhD supervisor, and it's a great pleasure to introduce him. So he's going to talk about local symmetries and geometry of curves and surfaces.
Thank you very much, Farid. Well, first of all, to say that it is a great pleasure and a great privilege to be back here at this Singularities meeting. So, who's here? Is it Maria? But who is so charming? It's Maria del Carmen. Who is our hero? Maria del Carmen Ramiro. Is she really 60? Can we trust her? Yes, it's Maria del Carmen Ramiro Foster. Happy birthday. So here's the plan. I'll talk a little bit about some early mathematical work from about the 1980s onwards on local symmetries, mostly reflectional symmetry, in which I was involved. But I shall mainly concentrate on talking about things to which I do not know the answer, rather than things to which I do. I'll mention here and there some applications which have been made by other people, and also to some extent by myself, to shape analysis and computer vision. And then I'll finish by talking about a different kind of symmetry, central symmetry, and that will be work with Stacek Inechko. So don't assume that you know anything about this, so this is going to be a very elementary talk. I'll start by saying something about so-called symmetry sets and medial axes of curves, and I shall not really talk about surfaces. Everything here generalizes, but it's so much easier to draw pictures for curves. So here's the general setup. Suppose we have a curve that's the red curve, and we consider lines, that's the blue line, which has the property that this reflects 2 points, P and Q, into one another, so that P is the reflection of Q and vice versa in the blue line. But furthermore, the tangent to the red curve at P is reflected into the tangent to the red curve at Q. Then we say that there is a local reflectional symmetry of the curve in that line. And this is the same thing as saying that there is a circle which is tangent to the red curve at these 2 points, and its center will lie on the blue line. So what we're looking at then here is circles which are tangent to a curve at more than 1 point, so-called bitangent circles. And in the case of a surface, then there would be, you have a red surface instead of a red curve. We would be looking at planes instead of lines, local planes of symmetry, and we would then be looking at spheres which have contact with the surface at more than 1 point. In that case, we can trace the centers of these bitangent circles, or we can also trace the midpoints of the chords, which join the points of contact of the circle. In each case, we obtain a locus in the plane. So the locus of the centers of the circles, or the locus of the midpoints of the chords, in some sense captures some aspects of this local symmetry. Or in the case of surfaces, then you would still consider the midpoints of the chords or the centers of the spheres which have contact at more than one place. We can also restrict to circles or spheres which lie entirely inside the curve, which I will always take to be smooth and compact, or which lie entirely inside the surface, that is, inside the region bounded by the surface, or inside the plane region bounded by the curve. The locus of centers of all the bitangent circles is called the symmetry set. The locus of centers of bitangent circles entirely inside the curve is called the Bloom medial axis, or the skeleton. And the locus of the midpoints of the chords of bitangent circles is called the mid-locus, or the smooth local symmetries, as its original name when it was first discussed by Michael Brady many years ago. So the medial axis, here's a very simple example. The curve, of course, does not have to be convex in order to make these definitions. But I've given a convex example, just an ellipse. So the medial axis is the centers of the interior bitangent circles, the locus of centers of interior bitangent circles. The symmetry set contains the medial axis, but it also includes the centers of circles which are not necessarily interior, so like the circle illustrated there. So the symmetry set, I think it's this. Where's the little red line? Is it there? Oh, come back. So where are we? Symmetry set, is it this one? Which is the little, there we are, thank you, yeah. So the symmetry set here consists of both these lines. Of course, in general, it won't be straight lines. The medial axis has just this line, so it's part of the symmetry set. And the mid-locus consists of the midpoints of all chords of all bitangent circles, so the midpoints, and therefore this extends out to the end here. So it extends right out to the ends of the ellipse, because you're looking at the midpoints of the chords. The endpoints of the medial axis, or the symmetry set, or the mid-locus, correspond to vertices. That is, places where the two contact points have coincided, and so the contact between the circle is then 2 plus 2, which is 4, and that means that the endpoints are vertices, that is, maxima or minima of curvature at which there is a circle with 4-point contact. So the endpoints, like that. So all these endpoints, they correspond to vertices. So it's either the center of the circle or it's actually at the vertex. The way these are studied mathematically, but this talk is not actually going to include very many formulas. The way they're studied mathematically is by identifying the symmetry set together with the evolute, or the focal set for a surface. The evolute is this cuspy thing going round there, which is the locus of centers of circles having 3-point contact with the curve, the locus of centers of curvature of the curve M, and that has cusps at the ends of the symmetry set, where the contact between the circle is 4, so it goes up by 1 from the generic value. And this is studied, so there's the symmetry set, and the evolute is the cuspy thing, 4-cusped curve going round. So, this is the family of distance squared functions on the curve, or more generally on surface or hypersurface, and so it's the function of the variables which lie in the ambient space. Here, just for a curve, it's in the plane, and P is a point on the curve, and we simply measure the square of the distance between those two. And then as this construction goes back to René Thom, we then look at the set of points in the plane for which this has a degenerate singularity at some point P, or else two singularities at the same level. And this, it's not difficult to check. This is exactly the set of, it's exactly the symmetry set together with the evolute, or the symmetry set together with the focal set for a surface in 3 space. So this is how it's done mathematically, and then you can study these as a well-developed theory of these so-called bifurcation sets of families of functions, and you can apply this to produce lots of general results about not just the symmetry sets, but the way they evolve, and I'll say a little bit about that. So the medial axis has a tree structure. In 3 dimensions, it has a more complicated structure than just a tree, but I won't go into that here. So it has a tree structure, and these are this fish shape. These straight lines are the lines joining, each of these is the center of a circle interior to the shape, and you join them up to the places where the circle is tangent to the shape. And this tree structure so has triple points, and the triple points, or the Y junction points, because they resembles the letter Y, and these are simply the centers of tritangent circles. So that's where 3 branches meet. On the symmetry set, this Y junction becomes a complete triple crossing, because you can continue the circles beyond there, and they start to go outside, but you don't mind that for the symmetry set. Symmetry set has quite a complicated structure. So here the dark line here is the curve, which, again for this example, is just a convex curve, doesn't have to be convex. And the symmetry set is this rather complicated thin line, together, which includes also the 3 thick lines, which are the medial axis. Medial axis is always part of the symmetry set. Medial axis consists of the centers of circles which are bitangent to the curve and interior to it. And that the symmetry set augments that by centers of circles which are bitangent but not necessarily interior. So the symmetry set has this rather complicated structure, and in particular it has cusps, like this point. That's a point on the symmetry set, and that's a cusp point, and has cusps, and these are the centers of circles. So there's this circle which is tangent at one point down here. It's tangent here, but it osculates at this place. That means it has 3-point contact. So it's tangent and crosses. It is, in fact, the circle of curvature at that point. So when this happens, when you have a circle which is the circle of curvature at one place and also tangent somewhere else, then the symmetry set acquires a cusp. Whoops, come back. The medial axis which is the bold line here, just consists of these 3 branches, which somehow tells you that there are 3 bumps on the original curve that sort of sticks out in 3 directions. But the symmetry set has much more, let's say, complicated, or perhaps to say, make it more positive, more rich structure, and that it has this additional structure of the cusps. And so all these local symmetry constructions, as you can see, are to do with contact with circles or with spheres in 3 dimensions. The mid-locus, on the other hand, the locus of centers of chords of contact of bitangent circles, it has certain nice properties, such as it's generically free from cusps, it's generically smooth, but it looks sort of a bit odd, looks sort of rather strange, let's say. Sorry, just go back there. So it's this strange array of array of curves inside. It still ends in the vertices of the original curve, so these are all vertices of the original curve. Now the thing up here is called the pre-symmetry set, and this is more primitive. It records only the pairs of points of contact, the pairs of contact points. So it doesn't record either the center of the circle or the midpoint of the chord. It just records the pairs of points of contact. So, for instance, if you have a circle there that's bitangent, then it's, say, bitangent at 2 points which have parameter values t1 and t2, then on this diagram up here, which is on the in the t1, t2 plane, that pair of points is recorded twice because it's recorded as t1, t2 and as t2, t1. So it's symmetric in the diagonal. And also, you can think of this diagram up here as the left-hand side being identified with the right-hand side, because it's a closed curve, and the bottom being identified with the top. So it's really a torus, and the opposite sides are identified to form a torus, and then this collection of curves here is called the pre-symmetry set. So it merely records the pairs of parameter values at which there is a bitangent circle. So this one, if you look here, this is actually a contractible loop on the torus, and this is another contractible loop on the torus, that is to say, it contracts to a point. But this one going down here is an essential loop, that is, it represents a non-zero element of the homology of the torus, and there's another one here which comes down there and then completes by this. Remember, the bottom is identified with the top and the left with the right. So there are two essential loops in this pre-symmetry set, and there are a number of contractible loops. Well, it's a general statement that most mathematicians believe, and all computer scientists know, that the number of essential loops on the pre-symmetry set is always 2 or 0. Here's a fishy example. This shows an evolution of a curve, one of the standard ways in which a curve can be evolved along its normals according to the curvature of the curve, and you can see the gradual simplification of the pre-symmetry set on the right. Sorry, go back. I'm getting a... Right, so you can see the evolution of the pre-symmetry set on the right from something very complicated, but through very simple transitions to a situation where there are exactly 2 essential loops. That's the case of an ellipse. So the pre-symmetry set evolves to that of an ellipse, which has just 2 essential loops and no other loops at all. 2 things I'll just tell you which are not completely clear in my mind, one of which is it really true? That is what all computer scientists know actually true, that there are either, sorry, I've not got the hang of this yet, that there are either 2 or no essential loops on the pre-symmetry set of a smooth closed curve. Examples are known of both cases. I mean, most examples have got 2 essential loops, like the ellipse, but there are examples of cases where there's no essential loops. This was one. I mean, I've just indicated the curve there, and this is a rather complicated pre-symmetry set which actually has no essential loops on it. But Sergei Tapachnikov in 2011, I think it was maybe published a year later in the American Mathematical Monthly, found an example of a convex curve which has no essential loops. He did it in a very interesting way, which I'll only describe by waving my hands, that he identified, he showed that you can find a convex curve in the plane, which has the following property. If you take a point outside a convex curve, there's exactly 2 tangents to the curve. And they may or may not have the same length. What he showed was that you can find a convex curve in the plane so that you can completely circumnavigate that convex curve with a loop going right round it in such a way that the two tangents never have the same length. And that's actually, think about it, a little surprising that you can find such examples. So the two tangents never have the same length. And a little bit of interpretation, reinterpretation, tells you that actually this shows that that particular curve has no essential loops. Equal tangents from a point, of course the points of contact will then be also points of contact of a bitangent circle. So it's clear that there is some connection there. But I won't go into it. It's a very interesting example anyway, which he published in the American Mathematical Monthly. So this one has no essential loops, but it's certainly not convex. Another sort of slightly odd question, really. Is it possible to make any mathematical sense of the sort of the medial mid-locus, or the inner mid-locus? If you look at midpoints of chords and restrict to circles that lie entirely inside, then you get a rather unfortunate thing happening with the tritangent circles like this, because if you imagine you've got circles inside here, and these are the midpoints of the chords of contact. But then when you hit this place, which is the center of this tritangent circle, you don't know where to go, because if you stick to circles inside, this circle has got to move this way or it's got to move that way. So there's a discontinuity in the midpoints of the chords. And I don't really know if there's any way to get around that in a sensible way. So the mid-locus as a tool in computer vision has rather fallen out of favor, I think, because it has this rather unfortunate discontinuity property. The way in which symmetry sets of curves, if you change the shape of the curve, then of course the symmetry set changes. The pre-symmetry set changes, like in the fish example that I just showed you, and correspondingly the symmetry set itself changes in its characteristics, in perhaps the number of cusps, the number of triple points, all that. And these were worked out. Bill Bruce and I worked out all these transitions in about 1985. And actually, also Ilya Bogievsky has listed the transitions on the 3D medial axis and symmetry set for generic families of surfaces, but I'm sticking here to curves. So generic one-parameter families of smooth curves, if a curve evolves in shape staying smooth, so never acquiring singularities, then the way in which the symmetry set can change is well documented. All the possible transitions and lots of interesting examples have been worked out. So we can say, for example, in this case, we can say not only how the pre-symmetry set here changes, but we can say exactly how the symmetry set is changing at the same time. But there are other very natural families of curves which pass through a singular member. For example, if we take a smooth surface in three-dimensional space and we take tangent plane to that surface, and then we displace that tangent plane a little bit in either direction, then the curve of intersection of that plane with the surface will pass through a singular member. In the case of a convex surface, of course, it would just go through a point when there's tangent. But if it's a hyperbolic point on the surface, then it will go through two intersecting curves. And the motivation for studying these goes back a few years. It was actually to study the geometry of isophotes, that's equal intensity curves of an image. So it did come from an application. So here's an example. This is work with André Diatta and Ricardo Rubi Vargas. So here's a surface over here which has an umbilic point at the bottom. And what I've drawn, this is a perspective view of it, what I've drawn is lots of sections of the surface quite close to that tangent plane. So when the intersection with the tangent plane is one point, but as you displace it slightly upwards, then you get these curves, which in fact always have 6 vertices. This is a standard result, that the intersection of a plane parallel to the tangent plane at an umbilic acquires 6 vertices, and it starts off being very nearly circular, but nevertheless has 6 vertices, not infinitely many, and as you can see, it evolves in shape like this. So this is a contour map of the surface sections, and this is this planar surface sections drawn in perspective. An umbilic is a special point of if you haven't heard of them, for the spherical geometry of a surface. It's a place where the D4 contact with a sphere. So it's typically of this form, if we put it in Monge form, is typically z equals x squared plus y squared plus higher terms, and the cubic terms should not be divisible by x squared plus y squared to make it generic. The sections become more circular, that is, the sections where this is equal to a constant. So if z is a small positive constant, then we get these curves. If z is 0, then we get just the origin. If locally just the origin. If z is a small positive constant, we get these curves in the xy plane. So that's like just moving the tangent plane up a little bit. So there are 6 vertices, and so the medial axis has 3 endpoints, and the symmetry set has all 6 endpoints. You only get half as many for the medial axis, because they're only allowed circles which are contained inside the shape. So the symmetry sets of these plane sections of a surface close to the tangent plane at an umbilic, they must shrink to a point in some way, but how do they do it? The dark Y shape here, upside down Y, is the medial axis of this section close to the tangent plane at an umbilic, and the rest of this complicated thing is the medial axis, quite similar to another example that I showed. And here is an enlargement of the symmetry set. So it has this complicated structure in there. The medial axis just has the 3 branches. And this is just the pre-symmetry, so it happens to be part of the picture. So there seem to be 6 cusps, 1, 2, 3, 4, 5, 6, which says that for z sufficiently small and positive, the section z equals constant of the surface close to an umbilic should have 6 circles which are osculating at one place and tangent at another place, and it should have, as you can see from the picture, exactly 2 triple points. There's one which is on the medial axis, and here's the other which is not on the medial axis. So presumably they come from the tritangent circle. It's very plausible. You have a curve of this shape that there's one circle inside that's tritangent and one circle that's outside. It's tritangent. I've tried to draw them here. So here's the black curve is the original curve, and there's the tritangent circle inside and the tritangent circle outside. It's very reasonable that there should be 2 of them, and so there should be these 2 crossings, 2 triple crossings. But actually, I don't know how to prove rigorously that the symmetry set always has 2 triple crossings and there are exactly 6 cusps for z a sufficiently small positive number. The cusps, as I've said before, will be centers of circles which are tangent at one place and osculate at the other place. That is, they cross as well as tangent, 3-point contact, and each of those will contribute one of these cusps. The center of each of those circles will contribute one of those cusps. So extensive direct calculations certainly suggests that both of these are true, and also I've worked a little bit on this with a number of people who know a lot about algebraic geometry, and further extensive calculations certainly seem to suggest that there are always 6 of these circles, which are tangent at one place and osculate at another place as the curve, as the section gradually shrinks to a point, and that there are always triple crossings. And for example, one can calculate the locus of triple crossing points, and they appear to approach one another along the branches of an ordinary cusp. But I have no rigorous way, other than doing ghastly calculations in Maple, for actually asserting any of these things. So in general, when a family of curves passes through a singular member, here it's an isolated point, when you become actually the tangent plane at the umbilicus just intersects in a single point. That's the singular thing. After that is empty. Can we predict how the medial axis or the symmetry set behaves? There's one case where actually we can, and that's this one. So let's look at the sections of a surface which are parallel to the tangent plane and close to something called an elliptic cusp of Gauss. So a point of a surface is called a cusp of Gauss if the Gauss map, which is a map from 2 variables to 2 variables, has a cusp singularity. Various other descriptions of it, the tangent plane has exactly A3 contact with the surface there. It is actually possible to prove something here, but only by a complete fluke. So here's what it looks like if you just slightly raise the tangent plane at an elliptic cusp of Gauss. You get this sort of banana-shaped curve which emerges, and here's a selection of these planar sections of the surface as you gradually rise up. So this is for a very small value of z, and as you work outwards, these are very slightly larger positive values of z. Again, for z equals 0, it's actually an isolated point. So the surface here has the form, well, it has an x squared, and then there won't be any other. It's a parabolic point of the surface, so there's no other quadratic terms, and then there's some cubic terms and some degree 4 terms, and then the crucial thing is that a squared minus 4b should be less than 0. So this is just the way that elliptic cusps of Gauss are described. So when thinking about this with Uribe Vargas, I came across a paper in the Bulletin of the AMS in 1944 called Vertices of Plane Curves, and it has this extraordinary theorem in it, which says that suppose you have a plane curve with 4 vertices, and which is not necessarily convex. You see, these are not convex curves, as you can see. They're not convex. So let's think of a non-convex case. So it says that if you have a curve in the plane with 4 vertices, 4 extrema of curvature, exactly 4, and it has the property that if you look at the circles of curvature at the 2 minima of curvature, where are they on this thing? The 2 minima of curvature on this, one here and one here. And the maxima of curvature are here and here. So if you look at the circles of curvature at the 2 minima of curvature, and if these circles intersect, then you can invert this curve into a convex curve. And of course, it still has 4 vertices, because inversion is something that preserves circles, or the set of circles and lines. It preserves circles, and it preserves contact, so vertices go to vertices. So it has the theorem that you can show that if the circle of curvature here and here, if you can show they intersect, then you can invert this curve into a convex curve. And once you have a convex curve, it's very, very easy to check that you can't have tritangent circles. They require at least 6 vertices, and also with a little more care, you can even rule out circles which are which are osculating at one point and tangent at the other. So in fact, you can show that for this case, there are actually no cusps and no triple points, but it's a total fluke because of this theorem. So it means that the symmetry set of these plane sections close to an elliptic cusp of Gauss are extremely boring. They just consist, they just consist of a branch down here, which actually is the medial axis, together with another branch which starts at the center of curvature here and goes off to infinity. That's because of the inflections, and then comes back from infinity and ends at the center of curvature at the other minimum. So it's actually possible to predict what the symmetry sets are. They're extremely uninteresting. They have no cusps, no triple crossings. There are a number of other cases of families of curves containing a singular member where I don't know how the symmetry set evolves. For example, the plane sections of a surface close to the tangent plane at a hyperbolic cusp of Gauss. There's a difference between the hyperbolic cusp of Gauss. It's a sort of majority verdict in some sense about there are three places at which the tangent, which the normals to the surface are parallel, and if they are hyperbolic points, you call it a hyperbolic cusp of Gauss, and if they're elliptic points, you call it an elliptic cusp of Gauss. So, but I won't go into the technical difference. I just draw you a picture. There's the intersection of the surface actually with the tangent plane at a hyperbolic cusp of Gauss, and you can see the intersection consists of two tangential curves. At an ordinary hyperbolic point, the intersection is two transverse curves. Hyperbolic cusp of Gauss, the intersection is two tangential curves. And here's what happens if you move the tangent plane slightly up. You get this one curve over here, which has no inflections, and then you have a curve here which has got two inflections. So the sections look something like that. So you have here's this one together with the one on the other side is one section, and as you gradually move through the tangential curve, the tangential plane, they move through this, and then they switch into the top and the bottom one. So it's possible to predict exactly what the plane sections, what the vertices and the inflections are. You can prove this rigorously. You can describe exactly how many vertices and inflections, but I really don't know how to pin down what happens to the symmetry sets in this case. There seems to be no simple way of getting hold of it. But now, for the remaining time, I'd like to talk about something completely different. This is joint work with Sarchik and Nechko, and it illustrates a little piece of geometry that doesn't seem to come out of the standard ways of looking at surfaces. The standard things for surfaces are contact with spheres and planes, and they distinguish parabolic points and cusps of Gauss and vertices and umbilics and ridge points and such things. But this seems to pick out something rather different. So, I'm sorry, there's another formula here, but so let's take a point of a surface M, smooth surface in compact, smooth, embedded surface in 3 space, and suppose we reflect the surface in that point. So when you reflect something at a point, you take each point to the reflection in that point, same distance but the other side. So it's actually reflecting in a point, not in a plane. And it's not difficult. And then you look at the contact between the original surface and this reflected surface. And there's a good way of measuring contact between two surfaces. You parameterize one and you write the other one as the zeros of a function. You combine these two and you get a total contact function. So the contact function for any fixed p and q is this function of two variables, so it's a function of two variables. P and Q we regard as fixed for the moment. They're just the point at which we're reflecting, and this is a function of two variables. It's not difficult to show that this is the contact function. So the singularities of this function of two variables tell you how close the contact is between the surface and its reflection. And this is a two-parameter family of functions of two variables. The parameters being P and Q, they're the place you first thought of on the surface. And we can consider the critical set of this family of functions, which is just the points at which the derivatives with respect to x and y are both 0. And unfortunately, one of the difficulties here is that this contains all points of the form 0, 0, PQ. So this critical point, this critical set has a sort of trivial component, and in order to progress you have to somehow get round this. It's like sort of eliminating a diagonal, which is a very common thing to have to do when examining this kind of critical set. We can also consider the bifurcation set of this family of functions, which is the set of parameter values PQ for which for some xy there's a degenerate singularity, which means the first two derivatives, the first derivatives vanish, and the second derivatives, the Hessian matrix, is singular. So the critical set has two components. There's the trivial component, which consists of these points, 0, 0, PQ, and then there's another one. And it turns out that this is locally a smooth two-manifold. And it's parameterized. It lies in x, y, p, q space, and it turns out you can parameterize it by two of those variables, y and p, and so there's a particular kind of parameterization. But the interesting thing is that this turns out to be a function of y squared, and the bifurcation set of interest is the set of critical values of this projection. So it's where you take yp, the parameters on this non-trivial component of the critical set, and you take that to p, and then this function which you can calculate, but it turns out to be a function of y squared and p. And the set of points when y is 0 just turns out to be the parabolic set of M. So the parabolic set is contained in the bifurcation set of this family of functions. So studying the bifurcation set comes down to studying co-rank 1 boundary singularities. That just means that they're symmetric singularities. That is, they're a function of y squared here. So I've replaced y squared by capital Y, and so what we end up with is a function of y and p where we changes of coordinates have to preserve y equals 0. So this is quite a standard thing. Boundary singularities, you can look up what they mean if you haven't met them before, or symmetric singularities. Let's take the base point on the surface as the origin in Monge form, and we'll take the origin to be a parabolic point of M. Then this function q, you can calculate it. It turns out to just be determined by the higher coefficients in the expansion of the surface as just an x squared for the quadratic part, because this is a parabolic point of the surface. And then if a certain coefficient is not 0, that just means that the origin is not a cusp of Gauss, then you can calculate this function q, and it turns out to involve the coefficient of y to the 4th. So there's x squared plus, and then the next important thing is actually the coefficient of y to the 4th. And if that is not 0, then G is of the type local diffeomorphism. And if the coefficient of y cubed is not well, not 0, I'm just assuming that here because look, it comes in the denominator, but the coefficient of y to the 4th is 0, so this is missing, then there are higher terms, and the origin is then said to be an A2 star point of M. So what we're working at here is there's a parabol on the parabolic curve. There are special points which turn out they're not cusps of Gauss, but which something special happens when you look at this reflectional symmetry in the point. So along the parabolic, walk along the parabolic curve, you hit these special places where something special is happening, but it is not the something special which you detect by contact with planes or contact with spheres or anything like that. It's something quite different. And just in order to give it a name, we call this an A2 star point of M. An A2 point of M is just a parabolic point. It means that the tangent plane has A2 contact with the surface. So we call this an A2 star point of M. So for any non-cusp of Gauss parabolic points, the bifurcation set is the parabolic set only, but for these special A2 star points, the bifurcation set of this family of functions acquires an extra branch. So it looks like this, and this is familiar to people who've worked with boundary singularities. It's called a semifold. So the bifurcation set acquires this extra branch. So, and this point is a point on the parabolic set of the surface, but it's not a cusp of Gauss. It's not detected by spherical or plane geometry. It is something which is detected only by this special kind of reflection. These A2 star parabolic points are special then for reflection symmetries, but they're not detected by flat or spherical geometry. They have in fact arisen before, but in a much more mysterious way, and in the study of something called central symmetry sets, which I've studied in this particular case with the late lamented Vladimir Zakharyukin and a student of mine, Paul Warder, but I've also studied them with Staszek Janeczko, and this work is with him. Cusps of Gauss are not special. This bifurcation set doesn't notice them at all. And so as you walk through a cusp of Gauss, the bifurcation set remains just the parabolic curve. This approach, unlike that through center symmetry sets, actually allows us to determine how A2 star points are born and die. And this rough picture here, well, this is a picture of an actual example. I'm sorry, it's got a little bit fuzzy around there, but so here's the parabolic curve. The red curve is the parabolic curve on a surface, and the blue curve is this extra branch of the bifurcation set, and it ends at these two A2 star points. And as the shape of the surface changes, these two simply separate. It's hard to tell. This is an actual example, which is why I haven't fiddled it so that these look further apart. But this is called a semi-Beaks transition, and here's the parabolic curve, and the other branch of the bifurcation set is now completely separated from it, so that these two A2 star points have now disappeared in a pair. But the point at which they disappear is not special in any way for the flat or the spherical geometry. It's special for this kind of reflectional symmetry. And the other way in which they can occur, they can disappear or appear is through a semi-ellipse, where this here's the parabolic curve, and here is the extra branch, and this can simply shrink to a point, and these two collide and then disappear. This is the parabolic curve, so on one side there's elliptic points, on the other side there's hyperbolic points, but it could be either. This could be on the elliptic side or the hyperbolic side, so there's two different kinds of A2 star points. So the place where these coincide is still an ordinary parabolic point, each transition comes in two flavors, hyperbolic or elliptic, depending on which region the blue curves lie in, because they could be on either side of the parabolic curve. Well, so local reflectional symmetry distinguishes special points of a surface, shows how such points are created and the surface evolves. They are incidentally not created when a new branch of the parabolic set is created. And what our aim really is to try and study this geometry for surfaces in four space to see what special points turn up and how these might differ from the special points on surfaces in four space which arise through the flat or the spherical geometry. But in the meantime, so thank you for your attention.
Thank you, Peter. Any questions?
There may not be any answers, mind you, but... oh, Terry.
A long time ago, I was looking at projections of surfaces and R3 to planes.
You certainly were.
And they're, a long time ago. so there, besides the cusp of Gauss, there are other parabolic points that turned out to be important as well. And there was also no y to the fourth term there. Are these related to what's showing up in your...
Actually, I haven't a clue. I'd forgotten that.
Aha, it was a long time ago.
Yes. Goosebumps and no, I don't think they are. No, okay. I don't think so. No, I believe I have thought about that, and I think the answer is no.
Okay, so no. I'll look more carefully at your stuff.
Thank you, yes.
The other question I had was in the Tabachnikov example. Okay, so if you take this curve which has no essential loops, and you move in a generic way to an ellipse, there must be a transition point, probably serval. What happens to the essential loops there?
Well, the way in which these pre-symmetry sets evolve is basically through Morse transitions. Actually, I mean that they acquire a crossing, and then you can have two branches before which don't link up to form essential loops, but afterwards they do, the ones on the other side.
So what happens at the crossing? Is that
that's special. That's actually a bi-osculating circle. Yeah. Yeah, so special things happen. One can describe exactly what they are. Yeah.
And then just one last question.
Yes, sure.
I was looking at your picture of the mid-locus that you had there. Is there any relation between the mid-locus and the disentanglement of the central symmetry set?
I haven't the least idea. Okay. I'm sorry, but
because it looks. I could almost see those cusps disentangling them and getting.
Well, it does join the same pairs because it joins vertices. So, I mean, there is a sort of correspondence. I mean, there must be, because the circle, you've got the center, and then you've got the midpoint of the chord. So you can correspond points from the symmetry set onto the mid-locus. Yeah.
We have time for one more question or comment. No? All right. Thank you very much. All right. Just before you go for